Good. Good.
Okay. So today we plan first short recall on the T and F test. T-test plus F-test. You already know it, but we are in 2020 and we studied this in 2019, so you forgot everything. So just a short recall about T-test and F-test. Then we will calculate standard errors for forecasts, and we will learn how to construct interval forecasts. And third topic, I hope we will start and we will go as deep as possible into heteroscedasticity. What it is, how to find heteroscedasticity, how to test heteroscedasticity, and so on. Okay, so that's the plan for today. We will do every topic in R and by hands. Basically, that's all. I will start with T and F test. Okay, so first short recall on T-test. We have some assumptions and we have a model y beta 1 plus beta 2 times x plus beta 3 times z plus u. So there may be not 2 but 3, 4, 5, 17 regressors. Our assumptions are, there are many assumptions that will lead to validity of our results, but one of the setup is that observations are independent and identically distributed. That means x1 has the same distribution as x2, z1 has the same distribution as z5, x1 has the same distribution as x2, z1 has the same distribution as z7, and so on. So I don't say that 1 and x1 have the same distribution because x1 may be expenditures on TV advertisement, and z1 may be expenditures on internet advertisement of first enterprise and so on. Okay, second assumption is that this equation how y depends on x and z, and some assumptions about u. This u has zero mean, given all regressors. X means all regressors. I will finish assumptions and we will find some estimate. Variance of u given x is sigma squared. This assumption is called homoscedasticity. And later today we will see what happens when this assumption is violated. So we will first assume 0.4, and some moments later we will talk what will happen if the 0.4 is violated. 5. So independence. So there is a technical assumption. Regressors regressors are not linearly dependent. Then what else? I think that's pretty all. And 6, for example, 6 that U has normal distribution. I think that's all. And under these assumptions, under 1, 2, 6, we have stated that if I calculate beta hat minus true value of beta divided by something that is called the standard error of beta hat, this T statistic has which distribution? If it's T statistic, it has student. Yeah, right. It has student distribution with how many degrees of freedom?
N minus 1.
N minus k, because n is a number.
Yeah, number of parameters.
Number of observations, and k is the number of parameters of betas. So in my case, in my example, for this particular equation, in example, k is equal to in example, k equals to 3. So just first beta is counted as an honest full parameter, because sometimes in some books standard error of beta hat, standard error, SE means standard error, it's abbreviation of beta hat. Okay, that's in denominator. Okay. How to calculate this? We have supplied formulas for simple regression, for univariate regression, and for multivariate regression. We have said that we can use matrix algebra, but we have not provided formulas for. So you should understand that it exists, but for so how to calculate this standard error? Yeah, that's a good question. So if you have a very simple model like this, only beta times x plus u, so no beta 1, just one beta, so just one beta, univariate model. So in this case, you may calculate standard error of beta hat as a square root of RSS divided by n minus 1 times 1 over sum of xy squared. We have, I think, even proved this formula, but today I will just use it like this. In a more complex context, when you have bivariate regression, so you have beta 1 and beta 2. In this case, standard error of beta 2 hat equals to square root of RSS divided by n minus 2 times 1 or sum of xy minus h bar squared. And for more general case, I think yeah, that's good. Perfect. Okay. And the more general context, when we have more than 2 betas, we will rely on computer. Okay? So just let's calculate by hand, and then let's recall how to do this on computer. Just a small exercise. So for example, you have y hat equal, you have estimated the dependency of, I don't know, the number of cakes you have eaten, depending on the number of coffee cups you have, and the dependency is like this. 1 plus 0.5 times x. So it's a dependency between the number of cakes you have eaten and the x is the number of cup of coffee you drink. So, and standard errors are below, usually standard errors are denoted in reports below coefficients in brackets. So, for example, we have 0.3 standard error, and here 0.1. So these are standard errors. And let's imagine that you have 100 observations. You have asked 100 students about their consumption of coffee and their consumption of cakes. And you have estimated regression. And my question is, first question, tests a hypothesis that the number of cakes eaten does not depend on the number of cup of coffees. So test that beta x, this coefficient is 0 against hypothesis that beta x is not 0. Let's select confidence significance level 0.001%. So first test this hypothesis. And question B, provide 99% confidence interval for beta x. The first question tests the hypothesis whether the coefficient is 0. And the second, construct 99 confidence interval. Who can do this? This is just a recall, it's not new information. We have done it last year. It was, I understand that it was, I think, months ago, and you have a good holidays with Olivier and what else? Yeah, Azalika. Be brave. I will help if you. Just let's remove the assumptions. Because normal assumptions are necessary for math, but we are not using them, like, let's say, directly. Yeah, we. Nice,
Okay, so the formula for test statistic is this.
Только далеко не залезай, ты нахуй. Такое видео маленькое. Да, вот так. Perfect.
So here we have beta hat.
Yeah, that's important to understand that
That
0.5 is not a true beta.
Yes.
It's an estimate.
So it will be like this. And divided by standard error is 0.1. So it is 5.
Okay, and I will open T-table on
Yeah.
on computer. Just a moment.
And so T-critical we need to find.
But you may know approximately values for.
Well, actually, we have like 100, the number of observations, so it could be normal, approximately, because the sample is large. And so, but I don't remember actually for normal the Z critical. So I would appreciate if you tell me.
Yeah, just a moment. But you may remember plus or minus 2 will be 95%, yeah? And plus or minus 3 will be 1%, so it's okay. 5, you should roughly understand that plus minus 2
sigmas, yes, it's 99.
95 2 sigmas.
Oh, 2 sigmas 95, yes. And 1 sigma, oh, no, 99 is 3 sigmas, right?
99 is
Three
yeah,
sigmas,
roughly
yes.
3 sigmas. Okay, just a moment, I will provide. Okay, table.
And it is T alpha divided by 2 and minus K, right?
Yeah, in our case we have 2 betas.
No, I mean here, it's alpha divided by 2, right?
It depends on the notation.
But
it's not standardized, so in some sources you may encounter here the area to the right, so it depends on the book. So it's not standardized.
So I don't need to write this.
Yeah, you don't need to write this because in some books you may encounter like this. In other book, it's not standardized what the index for T distribution means. In this case, let's look at this table. We see
it is 2.576.
Yeah, it's a confidence level. So we look directly at 99%. Well, this is the first table I have found in Yandex. So it's 2.5. No, 6 to 6, but because this is normal distribution, for T distribution, if we believe in our 6 assumptions, so it depends on a little bit on the set of assumptions.
2, 6, yes.
Yeah.
Right.
If you believe that original U1, U2, U3, these random errors are, so if you believe that these random errors are normal, then this T statistic has T distribution. If you believe that it's not normal but identically distributed, a weak assumption, and you believe that 100 is enough for convergence, then you may use Z. The result will not.
But it's roughly the same.
Yeah, I agree.
So in the rejection rule, if I remember right, T statistic less than T critical, right?
No, it's better to draw. And draw the picture. So you have minus T critical plus T critical.
Yes, it depends which two.
So in the center, when T statistics is near 0, it means that beta hat, so just be reasonable. If T statistics is roughly 0, that means beta hat is roughly 0, yeah? Then you have no evidence to reject each node. Yeah? If beta hat is roughly 0, T statistics is 0, then you have no evidence, no supporting evidence to reject each node. So for these values of T statistics, each node is not rejected. And for big values of T statistics and for extremely negative values of T statistics, we reject each node. So the picture is like this. It's better to draw a picture. And in our case,
Reject.
let's use the picture. In our case, we
So in our case, if 5 is higher than 2.6, then we reject 0.
yeah. And in our case, it is 5.
Yes,
Yeah.
5 is higher than 2.626. So we're like in the rejection region.
Reject each node. Yeah, that's fine. And maybe the last topic, let's спасибо.
Все? А,
Да,
второй немного.
второй такой целый, который как бы все сделать. That's fine. Are you happy? It's fine. We can do point B. Construct 99 confidence interval. So we have point estimate 0.5. Beta hat equals to 0.5. But this 0.5, is it plus or minus 12, plus or minus 1 over 2, plus or minus 1 million? What's the precision of our result? Who can? Who is our last call? Спроси, it's to us. Be brave.
He's asking about why we have chosen 99%.
I like 99%. That basically,
Could we get alpha divided by 2, and when we have alpha in our case, it was 1%, yes?
you mean this this area was alpha over 2, 0, 0, 0, 5, 0.5%. So if you are worried about the area of the right tail, the area of the right tail was 1/2 of the percent of 1%, and the area of the left tail was also 1/2
Yes.
and the total area, what is alpha? Alpha is the total area of rejection region.
Yeah.
So it's probability of reject each node if each node is true. So it's the probability of rejection of each node. So the total probability of rejection is 1%. 1/2 of the probability is 1/2 of the percent. So basically, like this. But the table here is very simple. It gives me directly the confidence level. So if probability of rejection is 1%, then confidence level is 99%. Yeah, but if you look at the top of the table, so you see you have two lines here, one tail, two tails. Two tails, 1% is here. But it depends on the table. I prefer tables with pictures because they are more clarifying, but this one, the first I have found on the web was without picture, but with two choices, basically.
Okay, thank you.
Okay, who can create 99 confidence interval for beta? But
I'm not sure.
no one.
What's our mean in this slide?
Sorry?
What's the mean in our equation? Mean. Yeah. x bar here?
X bar, we don't know X bar, it's not supplied, we don't need it to solve point B, but X bar is
So I just
mean number of coffee cups.
so we just need this deviation
No,
plus
we
or
don't
minus what for the confidence interval. What
Yeah,
was
the
that?
confidence interval.
It's this part where you put plus or minus z times s over square root of n, right? Like
No,
No, standard
no.
error of beta.
We need a confidence interval. So if, but just once again, I will use the same formula. T equals to beta hat x minus beta x divided by standard error of beta hat x. The same formula that I used before. And just the same formula. That's the formula, nice for this formula. Okay, and I know that with probability 99%, this fraction lies between which two limits?
2.626.
Yeah, minus 2.6 and 2.6. That is with probability of 99%. Okay, so that follows the picture.
So we also have a standard error for beta x. It's 0.1, right?
Yeah, we don't need to. This information was how computer calculates the standard error of beta hat, but because it's provided, we don't need to use the formula with 1 over sum x y minus x bar because it's already provided there. We don't need to use the formula to calculate standard error of beta hat because beta hat is provided.
But if we rearrange this formula like what we have right now, we get rid of standard error, like from the denominator, we've got
exactly.
from minus 26 to 26.
Yeah, and we obtain beta x changes from, so if you just multiply by
10.
Denominator, you can extract beta x from this double inequality. Yeah?
Yep.
It's okay? I'm a right answer, or I need to extract it?
But it's just like the numerator that's left,
Yeah.
beta x hat minus beta x,
Yeah. Beta x
in between the minus 26 to 26.
minus 2.6 standard error of beta hat up to standard error of beta hat. Okay. So I just, from this double inequality, I extract this beta x. I extract, and I also have a double inequality. Left side of double inequality, right side of double inequality, and so on. Okay? Okay, okay, let's do this. So it's easy. So in my case, it's 0.5 minus 0.26 up to 0.5 plus 0.26. Okay, because standard error of beta is given. I don't need to calculate it. Okay, so we have a 99% confidence interval for beta. So let's use R to calculate it for multivariate regression. So I'll go to R script. As always, I start by attaching packages. So once, I understand that you forgot everything, so I just do it once again. Okay. So I think it was our, it was our previous. So I will try to, let's save our previous desktop. I will save and send attach. It was session 3R, yeah. And it was T and X. we just go quickly over the same topic. So we just quickly attach packages. Library test. I think that's all the and I will use some built-in data set. Let's use another one. Let's use, for example, what I like to use. This is time series. I'd like to use some real data. What else? Life cycle series. Now. And what is US? Yeah, we may do something for it. Yeah. Let's predict the number of murders given urban population. So let's simple regression. Model 0 equals to LM. Data from built-in data set is errors. And the model is murder depends on urban population. Okay? So to use some real data. And we can look at the summary of model 0. So in our case, the number of murders depends. So we have estimate and standard errors in the table, 6.4 plus 0.02 times urban population, and standard errors are 2.9